We've learned about the formation of covalent and ionic bonds, and this lecture is going to talk about the polarity of these bonds. Polarity simply means there's some degree of separation of charge. So if you look at this example of a purely nonpolar covalent bond where the electrons are shared equally, there is no development of even a partial charge. Then let's look over, it's still a covalent bond, but the electrons are skewed a little bit. They're a little bit closer to one of the bonding atoms than the other. And because of that, there is a partial charge development. And then, of course, an ionic bond is the extreme of polarity where there's full development of charge. The polarity of a bond is really lies on a continuum where on one end we have pure covalent, and that's where the electrons, the bonding electrons, are shared completely equally. And then polarity increases until we get to the other extreme, which is ionic. And the dividing point between covalent and ionic is somewhat arbitrary. You'll see a little bit of wiggle room from different sources. And the new term here for us is that we've said before that covalent bonds are equal or sharing of electrons. So it turns out that in a covalent bond, there can either be equal sharing, in which case we call it a nonpolar covalent bond, which, again, you don't see any charge development or not significant charge development. And then we have unequal sharing. So that means that the bonding electrons lie a little bit closer to one atom than to the other involved in the bond. And then, of course, the extreme of polarity is the ionic bond. In order to understand bond polarity, we need to look at electronegativity of the atoms involved in bonding. So electronegativity is simply how much an atom wants extra electrons, okay? So the more strongly an atom attracts bonding electrons, the more electronegative it is. The trend of electronegativity, it's lowest in the lower left-hand corner, so that's down by cesium. And its highest, this shouldn't go into the noble gases at all. Fluorine is the most electronegative atom on the entire periodic table. And notice that the noble gases have zero electronegativity. If you look at this version, they're just completely left off. And that's because they have a full outer shell, okay? They have no attraction for extra electrons. So it is the difference in electronegativity. That's an important clarification. It's the difference in electronegativity between the two bonding atoms that determines how polar that bond is. The larger the difference in electronegativity, the more polar the bond. And that makes sense. If you look at this image, let's say that we have, and one of the atoms bonding is very electronegative. We'll just say fluorine, okay? And then let's say the other atom bonding is not very electronegative, so we'll say hydrogen. So the bonding electrons are going to spend more time nearer to the fluorine because it's going to have a stronger attraction for them. And because of that, you end up with some separation of charge. You would put what we call a partial negative charge over the more electronegative atom and a partial positive charge over the less electronegative atom. So this would be a perfect example of a polar covalent bond. It is not ionic. Anytime you see these lines representing a bond, that is a covalent bond. For ionic compounds, we don't draw lines connecting two atoms. So you can look here at some electronegativity values versus the polarity of the bond it makes. Alrighty, so the dividing lines between nonpolar, polar, and ionic that we're going to work with are as follows, but you may see them slightly different from different sources. So if the difference in electronegativity is less than or equal to 0.4 units, we're going to call that a nonpolar covalent bond. And by the way, you need to commit these to memory, so I would jot them down. And let's see, if the difference in electronegativity between two bonding atoms is between 0.4 but less than 2, we will call that a polar covalent bond. And all polar covalent bonds require a little bit more work. They are said to have a dipole, just another way to say they're polar. And you then need to show your reader in what direction the dipole points. You can do that either with an arrow, where the head of the arrow is over the more electronegative atom, and we'll go over that more later, or you can use those partial charges that I showed you a minute ago. All right, so if the electronegativity difference is 2 or greater, that is an ionic bond. All right, so this is just kind of a sidestep. What is a great example of a completely nonpolar bond? We call that a pure covalent bond where there's no evidence of any charge development or unequal sharing. The diatomic elements would be, right? There's 0 electronegativity difference for diatomics, 2 of the same thing. And so you've probably already memorized these from previous units, but if not, it's pretty important to do so. All right, so here's that continuum I was talking about where there's not a clear division between nonpolar and polar and between polar and ionic. So you might see some sources calling, instead of 2, the dividing line, they might call it 1.8 or something, but we're going to go with 2. If you have an ionic bond, you need to show, if asked, full charges for the cation and anion. And anytime you have a polar covalent bond, if asked, you show either these partial negative and positive signs, the partial negative going over the more electronegative atom, or you can show, instead of the partial charges, a dipole, where the arrow is next to the more electronegative atom. So there is such a thing called a table of electronegativity, and it was developed by Linus Pauling, and this is it. So he basically assigned fluorine, which is the most electronegative atom, an arbitrary electronegative value of 4, and everything else is relative to that. So you can see that cesium down here in the left corner, lower left corner, has the lowest electronegativity. And a trend that's important to know is that the farther apart 2 atoms are on the periodic table, in general, the more polar the bond's going to be. That makes sense, right? Because we have low electronegativity in general on the left side of the periodic table and high electronegativity on the right side of the periodic table. And so if you randomly pick an atom from the left side and an atom from the right side, you're going to get a polar bond. And the farther away from each other they are, the more polar they are. Let's look if we were to bond between carbon and nitrogen. They're right next to each other. They're not ionic anymore. If you pick any over here, you're going to make an ionic bond. But this would still be polar covalent. All right, so challenge yourself. See if you can do this without looking at that chart, but just by their placement on the periodic table. See if you can rank these 4 from lowest polarity to highest polarity. And I would suggest turning off the video, see if you can do it on your own, and then I'll go over it. Alrighty, so hopefully this jumped out at you as the least polar, okay? That would have an electronegativity difference of 0. So that is the least polar. And this is the most polar because it's ionic. So I'm kind of setting my range. So I'm going to put NaCl as the most polar. And now we have to choose between HBr and hydrogen fluoride. And so well, you already know fluorine's the most electronegative atom on the entire periodic table. So that means that there's going to be the largest difference between hydrogen and fluorine and hydrogen and bromine. And if you want to double check that, go back to the electronegativity table to prove it to yourself. So we have fluorine first, then hydrogen bromide, monobromide, then hydrogen fluoride, and finally sodium chloride. All right, so polar covalent bonds require the most effort on your part to describe. Again, if you have a polar covalent bond, you typically need to indicate to your reader where the partial negative charge is and where the partial positive charge is. Remember, the partial negative goes over the more electronegative atom, and the partial positive goes over the less electronegative atom. You can, alternative to those charges, draw a dipole. It's just an arrow that points, the point of which is next to the more electronegative atom. You may also, if it is a discussion about polar bonds, you may also see reference to what we call a dipole moment. Now, there's a formula to calculate these values, which you're not going to have to use the formula, but I do want you to know that the more polar a bond is, the higher the dipole moment. So lithium fluoride, for example, is the only ionic compound on this table, and it's the most polar. It has the highest dipole moment. And of course, as you would expect, a diatomic has no dipole moment at all, not polar at all. Alrighty, so to give you an example of how you can actually calculate the electronegativity difference for a bond. Sometimes you don't need the table of values. You can look, as we did a couple slides ago, on how far apart two atoms are in the periodic table. But let's do some examples actually using the calculation. So strontium and fluorine. Okay, so let's locate them on the periodic table. There's strontium, there's fluorine. I would say a really good guess would be that it's polar or ionic, right? But let's double check the difference in electronegativity values. Strontium has electronegativity value of 1. Fluorine is 4. And so the difference in those values is 3. Remember that anything 2 or above is ionic. So that is, in fact, an ionic bond. Nitrogen and chlorine. That one's a little surprising. You might look and say, polar maybe? But check this out. Nitrogen is 3 and chlorine is 3. They have the same electronegativities. So this bond is, whoops, I should have put nonpolar covalent. All right, and the last one, nitrogen and oxygen. Nitrogen is 3 again, oxygen is 3.5. So that is just barely polar covalent. So that one would have to be drawn with partial charges or a dipole. All right, see if you can do these. Rank these yourself using the table of electronegativity values a couple slides back, and we'll see what you got. I would suggest turning off the video and trying to do it yourself. All right, how'd you do? Here are the bonds that were shown in the last question, the previous slide. I then looked at the table of electronegativity values and calculated the difference. Now I want to point out at this point, notice that I've always come up with a positive electronegativity difference. When you're looking for the difference in electronegativity, it's the absolute value of. In other words, just always positive, okay? So if you get a negative, just ignore it. So let's go ahead and classify these. Wow, lithium fluoride, as we expected, is ionic. Carbon and bromine, if they make a bond, are nonpolar covalent. So make sure that you memorize these ranges, okay? Aluminum sulfide, interesting, metal and a non-metal, but guess what? It is not ionic. It's got to have a bond electronegativity difference of 2 to be ionic. So this is your first introduction to the fact you've always been told that ionic, anytime you have a metal and a non-metal, it's ionic. There are some exceptions because of electronegativity. Carbon and hydrogen bonds, we call those hydrocarbons, are nonpolar covalent. That's a good one to memorize because hydrocarbons are present all over the place. Gasoline, wax, oil, and so those are all nonpolar substances, and that's why things like gas and oil don't mix with water, which is very polar. You'll learn later that polar substances prefer other polar substances, and nonpolar substances prefer other nonpolar substances. So here's another ionic, metal and nonmetal. And finally, again, oxygen and nitrogen, just barely polar covalent. And so you would need to go then probably and assign either partial charges or dipole. So you could put a negative partial charge over all the more electronegative atoms. Or, and then the partial positive or the less electronegative, or you could draw the dipole. All right, almost done with this lecture. Why are we making such a big deal about bond polarity? Because the bond polarity is a really important factor in determining the overall polarity of a molecule. Because let's say that we have a polar bond. We know opposite charges attract, and so if you have a polar substance, it's going to attract each other pretty tightly, and that's going to affect its arrangement with each other and what we call intermolecular forces, which affects a ton of properties. Here are just some of them. The degree at which, temperature at which something changes phases is highly dependent on how polar the substance is, how attracted molecules are to each other, again called intermolecular attractions, which we'll learn a lot more about a little bit later. But that is it for this lecture.